for you. We wanted you to go back and think about coplanar and collinear. Any questions on 1 through 6? The purpose of 7 through 12 was having you look at this diagram and review congruence markings for segments and angles. So if you know the distance from B to C, and if you are still struggling with what 2 capital letters put together means, you haven't been reviewing your notes, you haven't been studying, you haven't been putting your brain into what you should be learning about in geometry. The distance from B to C is 12. The distance from C to E is 15. Your job is to find BE. So you're using segment addition and those congruence conversations to figure out. I know that ray CG is the bisector of angle BCA because of those 2 congruence markings. I know I can set the distance from BC equal to the distance from CD and solve for X because of the congruence markings. If the distance from A to C is 5X minus 16 and C to F is 2X minus 4, then I know I can set them equal to each other, solve for X, and then plug that in to find out what the distance from A to F is. If angle BCG is 60, and angle GCA is also going to be 60 because they're congruent, and BCA is going to be their sum because of angle addition. If angle ACD is 60 and angle DCH is 20, that means that HCA is going to have a measurement of 40. Questions on that diagram? Here we have a lot of angle vocabulary. We wanted you to revisit the idea about supplementary, vertical, congruent, adjacent, congruent, complementary, supplementary, bisectors, and whatnot. Anybody have any questions on those that they couldn't figure out? Go.
The wording for 19 confused me a little bit.
All right, let's see. It says, 19 has nothing to do with that diagram. It just wants you to be able to take the information and write your own problems. So if it's easier for you when you're doing something like this, if you want to go ahead and call this X and this Y, if you want to say X plus Y is equal to 180 degrees as part of your first equation, and then you know that the measure of this one you said was Y is 20 degrees. So if I know the measure of angle Y is equal to 20, 20 degrees less than 3 times the measure. Hold on a minute, there's more to that. So let's just go ahead and call it Y. So if you know Y is equal to 20 degrees less than, that's one of those ones that translates backwards. 20 degrees less than 3 times the measure of ABC, which is what X is. This is what we've been trying to get you to review by giving you a system of equations. Anytime you have 2 unknown variables and 2 equations, you can use one to solve the other. So this one here goes in for Y. So your new equation that you can write is X plus what Y is equal to 180. And I'm going to go ahead and write 3x minus 20 in here. So that's going to give me 4x's is going to be equal to 200 because I added 20 to each side. So I get 1x has a value of 50. So when they want me to figure out what are the measures of the angles, then I can go back in if x is equal to 50. So I know that then the measure of angle ABC is going to be 50 degrees. And then the measure of angle DEF is going to be equal to its supplement, which is 130.
Okay.
Sound okay?
Yeah.
Anything else? Did you have a question at the beginning?
More for
Okay.
Go ahead, question.
Go ahead.
For 18, what do you do for what are measure of angle X?
So same thing. These 2 angles are complementary angles. So if you want to call this X and this Y, you can. So when I talk about measure of angle x, y, z is 3x plus 9, that means that 3x plus 9 plus this angle here, 5x plus 9 together equal 90 degrees. So once I figure out what they're equal to, 8x plus 18 is equal to 90. 8x is going to be equal to, what's that, 72? So what's that, x is equal to 9? So once you figure out what x is equal to, you can go ahead and plug that in for both of those x's and get the angle measures. Anything else on this worksheet? All right, again with distance, midpoint, and slope. So we're hoping that at some point it sticks in. Matthew, put your head up. I'm hoping that at some point in time, distance, midpoint clicks, because we're going to continue putting things on the coordinate plane, and we're going to continue having to find the midpoint for 22. The midpoint wasn't on there, so if you need to look at that answer, you can. All right, the unit numbers are a little off because our unit 0, we added that in. Believe it or not, everything we did in unit 0, the county says you were supposed to know ahead of time. Our first unit was supposed to be all of this stuff with logic and P's and Q's and whatnot. So we snuck the unit 0 in because that's why it didn't count as a summative. That's why the unit numbers are off, because if we had started teaching you the way the county wanted us to, we would have never talked about unit 0. All that stuff that is in there, you should have already known walking through the front door. Crazy, right? Go ahead.
For 22, the midpoint you just talked about, wouldn't it be negative 1 half?
Ooh, I think it is negative 1/2, because negative 7 plus 6 is negative 1 over 2. Yeah, you can put Smarty up. Thank you, Jonah. There you go. So that's why the unit numbers are off. Can you imagine if we expected you to know all that stuff that we spent time teaching you in unit 0? The county thinks you knew that leaving algebra. Isn't that crazy? All right, so we really know that this is our unit 1 here. That's okay. Hypothesis conclusion. Your hypothesis always follows the if. So in this case, the sentences are written in a standard form, but be ready for the conversation to be, Dan needs glasses if he's nearsighted. So take a look at 26. If we switch the sentence around, Dan needs glasses if he's nearsighted. If he's nearsighted is still the hypothesis. That's still my P. Even though the order of the sentence was switched, that's okay. It's still our hypothesis always follows the if. Here you're supposed to write the conditional form and then the converse. If the converse was true, write it as a biconditional. So read my answers and see if we agree. For 31 through 34, that was that conversation about my Lala detachment or my Lala syllogism. And what's interesting is what I have here in the brackets, that's my conclusion that I'm seeing if it's validated by that law. So Sean, or no, it's not my conclusion. It's my fact that I'm given that then sets the law into motion. Shauna wakes up early. All right, if Shauna wakes up early, she'll be ready for her meeting. If she's early for her meeting, she'll gain a promotion. So guess what? Shauna's getting her promotion. Because P is true, Q is true. Because Q is true, R is true. Rock on for Shauna. And what's weird about each of these is our P is a part of our second conversation. But if Linda practices, her band's going to win the contest. If her band wins the contest, they're going to win that $500. So as soon as you know that Linda's practicing, you know they're getting $500. As soon as you know Brendan stays after school, he's going to make chorus. So having that law of detachment and law of syllogism practice was important, especially for my friends that are still planning on retaking, which you left off to the last possible moment. For Unit 1, the deadline's tomorrow after school. Any questions on any of that? You can't continue to kick the can down the road and put off learning what we need you to. It's making the course too hard for you. And that's not fair. Nobody wants to be in a course that's too hard for them. All right, I gave you a couple of poems yesterday, or last class. Your warm-up was this symmetry one with the log-on instructions in the back. What the secretary say to her boyfriend? Anybody get it? You are just my type. So that's going to be a symmetry conversation, a nice little warm-up. Again, the county says you already know all that stuff. Why did the couple get rid of their waterbed? They were drifting apart. Come on, that's funny. What did the lumberjack do after cutting down a tree? He took a bow. He took a bow as in, look at what I did. And then the way that they spell it, that's like the bow of a tree. And who has red hair and no parents and barks? Little Orphan Annie. So it's a play on Little Orphan Annie. But it's Orphan because of the dog. Okay. Again, when you choose to do no homework, you are making a choice to live in a cloud of frustration and misunderstanding and failure. It's that simple. None of these worksheets were too hard for you, but they were a critical review for all the stuff we're doing next. And if you said no thank you to that, don't be surprised when everybody in the class seems to be doing well and understanding stuff that you're struggling with. I don't know how to say that enough times. So we started off with including map testing just in case you were upset about the passage of time. Wait a minute, what did we do last class? We did that map testing and you had your pizzazz worksheets as review. If you are a friend who did not do any of that work, I suggest you doing it because that's like if you missed soccer practice, you missed out on some important practice that everyone else got. Today we are starting in a unit called Symmetry and Transformations. Today we're going to talk about translations, rotations, and reflections. There's some pretty cool widgets on MathSpace that I'm going to show you. You're going to finish the practice in the packet, and then you're going to work on Delta Math. There are 3 separate Delta Maths, one for translations, one for rotations, and one for reflections. So make sure that you pop open all 3. Next class, we get out 2 hours early, so we're definitely going to talk about symmetry. I hope we get to dilations and scale factor. If not, we'll just bump that down to our sequences of transformations. We're going to combine that with the review because the sequences of transformations put all of these in order together. You have a summative test now. It feels like it's a long time away on the 12th and 13th, but there's a lot of days off in between. So we have a half day on Thursday, a holiday on Friday, teacher work days on Monday, Tuesday. We'll have class on that 7th here, and then your test is going to be next class, and it is a summative test. No formative quiz for this one. Is that what you're going to ask? So your formative, as far as, hey, how am I doing? Delta Math will provide that feedback for you. The Delta Math in this unit is pretty cool. Again, your concept summary, things that you need to keep track of to know. Please take the time to do that. As you're studying. You've heard me say this before, but it definitely applies to this one. There is more math content per square centimeter of paper in a text or in notes than in any other subject. More content jammed in per square centimeter than English, science, and social studies and foreign language. If you take a look at just this first part of the sentence, take a look at all the vocabulary that is necessary for you to know. A transformation is an operation that maps or moves a pre-image, the original figure, onto the image, the new figure. If the pre-image is A, then the image is A prime, red is A primed. 4 basic types of transformations in a plane are translations, rotations, reflections, and dilations. Translations are slides, reflections are flips, rotations are turns, and dilations are reductions and enlargement. Would you do me a favor and just turn to your partner and count how many vocabulary terms you think are just in those 2 ideas? Turn to your partner and count them out. Go. 1, 2, 3, 4, 5, 6. All right, we came up with 13. So see if you agree. A transformation. Now you may know what that means. When my kids were little, they played with a toy called Transformers, and it was a robot that became an airplane or something cool like that, right? So a transformation is some kind of change that ends up happening. When we talk about it being an operation that maps, maybe you don't understand what it means when we talk about maps. So if I have 2 calculators that look the same and I map one on top of the other, you can't see the second because see how they're identical? So if I held them straight in front of Trevor, he doesn't know how many calculators I'm holding. Now, if he's looking at it tilted, he can see the difference. But if you talk about your own hand, if you put one hand forward and one hand backward, your one hand maps onto the other one. So that motion of mapping means sliding and moving it to the point of where one covers up the other. That's that definition. What does it mean to map onto one another? You've moved it so they match up perfectly. Transformation is an operation that maps. Now your pre-image is going to be what came first. So let's say I have this as my pre-image, and then your image is going to be what is second. So whatever transformation that I would apply to this to map on top of that, that's that movement that I'm talking about. My original figure is my pre-image, and my image is the result of that pre-image being transformed. We're going to read this one as A and this one as A prime. So that prime notation is what we get when we go ahead and we put that little apostrophe looking mark up at the top. We read that as A prime. We have 4 basic types of transformations: a translation, reflection, rotation, and a dilation. If I'm translating something, if you think about the SL in that matching up with the SL, you can think of a slide. That's where I slide something over to be on top of something else. That's a slide. If you talk about a reflection, the FL in reflection will remind you of a flip. And what ends up happening sometimes is you're not necessarily looking at the same face. So if I start off and you're looking at the keys of the calculator and then I flip it vertically, or if I flip it over a horizontal axis, then you have the difference between a flip versus that reflection over whatever line of reflection. If you're looking at a rotation, that R matches that R in turn. That's where I take it and I turn it around the axis. So if I have a rotation, I'm gonna take something and I can take stuff both counterclockwise and clockwise. So depending on which way I'm turning, and I'm going to be rotating around a point. We'll talk about that today. Now, when I talk about a dilation, that's something different because notice I was able to talk about all of my, Matthew, are you with us? Your slides and your flips and your turns of your single calculators using these two congruent figures. Congruent meaning, Stephen? Same size and same shape. When I talk about a dilation, however, that changes something. So if you look at this calculator versus this one, exact same shape, but what's different? Absolutely, not even close to the same size. So whether this is my original and this is my image, I've done a reduction. If this is my pre-image and this is my image, it's what? An enlargement. So your dilation is going to be either multiplied or divided by some scale factor making something bigger or smaller. So here's this next crazy vocabulary word. We talk about transformations that are isometric. If they're isometries, that means that the new figures are congruent to the original. So when we talk about this concept of congruence, that means the same size and shape. That symbol we've been dealing with for a while, Charles, and we want to make sure that we know exactly what that symbol means. An equal sign with the curly on top. Charles, are you with me? Are you sure? Pick up a pencil, and write some notes. That congruent symbol is going to mean that it's the same size and the same shape. The three types of transformations that are isometric are translations, rotations, and reflections. We like to call them rigid transformations because the size and shape do not change. Obviously, with our dilations, we get bigger or smaller. For a translation, we slide the pre-image onto its image. For a reflection, we flip over a line of symmetry. For a rotation, we rotate around a specific point, and we include the degrees and whether it's clockwise or counterclockwise. Each of those things guarantees then isometry. Dilations are different because they produce an image that's similar, meaning the same shape but not the same size. The scale factor is going to be what determines whether your image is larger or smaller than your pre-image. If your scale factor is greater than 1, your image is going to be bigger. If your scale factor is smaller than 1, then that means your image is going to be smaller. Turn to your partner and identify each of the transformations included in the table. Turn and talk about it. Go. Alright, so when we translate things, we're going to translate their movement. Sometimes that movement is horizontal, sometimes it's vertical, and sometimes it goes on a diagonal, and we'll talk about all three. When we have a reflection, there's going to be that line of reflection that it is flipped over. When we have a dilation, we can recognize that each of these vertices corresponds, but I definitely have a shrinking. In this case, my scale factor is less than 1. When we talk about our rotation, what's going to happen is our shape is going to rotate and create an angle of rotation. So I can say that this smiley face was rotated 90 degrees, and I know that I went in a clockwise direction. If it follows the clock, from left to right, then that means that is clockwise. If its initial direction is from right to left, then that's going to be a counterclockwise story. All right. In number 2, the transformation in the graph is a reflection over the x-axis. So our x-axis is going to serve as our line of symmetry. This transformation is going over. When we talk about the word in, if it's easier for you to read over because it's a reflection in that axis, picture that axis being like a mirror. We use arrow notation to describe this transformation. We can say that this triangle RST was going to be flipped and reflected over this axis. What we end up with is each matching coordinate using our prime notation. So S and S prime are corresponding, T and T prime are corresponding, and R prime are corresponding. So think back to the word corresponding from our perpendicular or from our parallel lines unit. That means in matching positions. So R and I think I messed that up. Hold on a minute. You like that better?
Yes.
I do. So it's in corresponding position after that transformation. That's better. So when I name the image of RS after this, we have the line fix that. We have the line segment R prime S prime. When I have the pre-image of R prime T prime, that's going to be segment RT. We can do a couple transformations in the same coordinate plane. A second transformation, we would read it as double prime. So if I want to map a second reflection of this triangle, it's now going to be reflected over the y-axis. So I'm going to go ahead and recognize that this becomes my mirror, and this becomes my triangle. When I talk about corresponding vertices, and I flip it over, S double prime, T double prime, and R double prime. Over that y-axis. Are we okay on that? Go ahead and scoot your eyes over this and talk to your partner and be like, I knew this before I walked in the door, and today's the day I learned this. Charles, feel free to wake up Brian. Go. So when we talk about what we're going to do now is take each of these and break them down individually. So first we're going to talk about translations. A translation is an isometry that slides a figure in any direction without turning. So if you look here, I've got my happy face, and when I go to move my happy face, I can go ahead and I can move it vertically. I can move my happy face horizontally, but I can also move my happy face along a diagonal vector. And this diagonal vector becomes an important conversation in showing how we move things on the coordinate plane. Again, the change in geometry was huge once Euclid allowed his geometry. He was long dead. But until Rene Descartes came around and said, hey, I'm going to go ahead and do some things. my one that was magnetic, hold on. Where Euclid says, I'm gonna go ahead and put my geometry on the coordinate plane, and then we can assign coordinates to each of these and look at what happens to them. So when I slide, flip, and turn my shapes around, it's not always going to be strictly horizontal. It's not always going to be strictly vertical. But what I can do is I can go ahead and recognize and come up with a conversation about how this moves. And I'm going to go ahead and do it in terms of the change in X. Anybody think that sounds familiar? Versus our change in Y. Now, if I'm talking about my slope, I'm talking about the ratio of my change in Y over change in X. That's not this one. What else has us looking at changes in X's and changes in Y's?
Distance.
So the difference between vector notation and distance notation is that our changes in X's and Y's in vectors start somewhere and end up somewhere clearly. When we talk about the distance between my two erasers on this board, it's never negative. Because the distance from here to here is the same as the distance from here to here. Nobody cares what we're doing. When we're talking about movement, we need to know where did you start and where did you go and in what direction. If any of you ever watched The Incredibles, the vector, right? Distance and magnitude, right? He has direction and magnitude, right?
Despicable Me.
Despicable Me, is it?
Yeah.
Oh yeah, right? With his piranha gun. Do I have it right? So a translation is going to be an isometry that slides a figure in any direction, but there's no turning to it. Hey, there's two ways that we describe this. We can either use coordinate notation, and if I use coordinate notation, I'm talking about how my X and Y are changing. Now, if you understand, when we talk about slope, whether I'm going from here to here or here to here, nobody cares. Because slope is either going to be positive or negative. When I care about distance, if I go from here to here or here to here, nobody cares. Because my distance is always positive. But with vectors, you need to know where you're starting, where your pre-image is, and where you're going. Because if I drew this arrow instead, it's going to be negative. The blue arrow is moving positive from here to here. The green arrow is negative, moving from here to here. And that change in X and that change in Y are going to be a different conversation. Coordinate notation shows us directly what we're adding or subtracting to each of the X and Y values of my pre-image to get to my image. In vector notation, we take a shortcut and we go ahead and we just say, hey, we're going to use these new symbols. They're not parentheses, they're not brackets, they're not braces. And I just talked to Mr. Logan today. I'm like, what do you call those things? He's like, parentheses. I'm like, they're not parentheses. He's like, okay, braces. I'm like, they're not braces. He's like, brackets. I'm like, they're not brackets. What do you call them? I had a teacher years ago that called them chompers. And I hate that word. It sounds so stupid. But no one has given me a better word that has stuck with me. So these symbols here, because she calls them, one of the kids was like, they're like crab claws. And every time I do crab claws, people are like this. I'm like, it's not, it's just these. So like baby crab claws, I don't know. So when we're talking about how do we designate that notation, that vector notation is of course a shortcut. Because you know in mathematics, we like shortcuts. Here we go. Your initial point is always where you're starting. Your initial or your starting point of the vector is A, and your terminal point where you end up is B. The name of the vector is AB. Now what's interesting is you might not be able to see it here, but that symbol is like half of an arrowhead. So it's vector AB. The horizontal component of vector AB is going to be 3. And the vertical component of vector AB is going to be 5. Notice 1 plus 3 is 4 and 0 plus 5 is 5. So that's what A and B have been added to. If I want to write the coordinate notation of vector AB, I would go ahead and say the coordinates x and y are translated such that x is added to 3 and y is added to 5. We love shortcuts in mathematics, so instead we can use our chompers and say vector notation is 3, 5. In 1 and 2 below, I would like you to describe the translation both way, using coordinate notation and vector notation. Pay attention to which way the arrow's going, which is your pre-image and which is your image. Turn to your partner and say, do you get this? So if you're not careful, you're going to find yourself in a position where there's another notation you don't know what it means. So we want to make sure you're doing your homework. We want to make sure that you're studying your notes. Because if you saw this on a test, would you know that that is a vector that is translating a figure -7 horizontally and -2 vertically? Because we need to know that that shape is moving, and we have a couple context clues about why we know that it's moving in that direction. A, the little arrow tells us. Do you see the little arrow? Make sure your partner sees a little arrow. Point to it and be like, see this? The next thing that you know the next way you know to check and see is check your primes. Your pre-image is just A, B, C, D. Your image is A prime. So your second image, that result of that transformation is A prime, B prime, C prime, D prime. Your original has no marks on it. That's your pre-image. Your result is your image, and that can be confusing. So we want to make sure that you pay attention to that notation. Now this is your study packet. Somebody last class was like, do we need to write that down? I'm like, I don't know. Do you need to remember it? Do you get it? Does that, you're like, oh, duh, that makes sense? Or you're like, no, somebody remember this. So write it down. Because if I write it up there, you should write it, but you're allowed to write more. What if you need more? What if you're listening to me and you're like, oh, she just said that and I want to make sure I remember that. You quick write it down. You are taking more notes instead of falling asleep. Charles, wake up. Stand up. I'm tired of watching you fall asleep. It's too hard to stand up here and watch you guys asleep. Get some more sleep. Put your phones away and go to bed at a decent hour. That's it. It's at the end of the day for me too. You can sit down. 3, 4, and 5. I want you to write the vector, name it, and write its component form. Talk to your partner, go. So again, it's a really easy conversation for a kid that does their homework, for a kid that's paying attention, for the kid that memorizes or makes an effort to learn the notation. It's a super impossible thing for you to recall on your own. You have to pay attention to where the arrows are. Number 3, starts at M, ends at N. In order to get to M, I think I did this backwards. I did slope. Hold on.
Wait.
Hold on. In order to get from N to M, my horizontal component is 4, my vertical is -2. In order for me to get from P to Q, it's over 4 up 1. In order for me to get from R to S, it's over 0 down 4. Do I have it right now? Yes. Good. Anybody catch that mistake? Yeah? Matthew, did you?
Yeah.
You look this smart.
Okay.
That's 2 so far I've done backwards. Alright, so these are the kind of questions that you're gonna get.
So, is the vector the one with prime or without prime? Bless you. Thank you.
The vector is the result, the image is the result of the transformation. The transformation happens along the vector. So the vector is the direction and magnitude of the slide.
Gotcha.
Does that make sense?
Yeah.
Okay. So some of the ones you're gonna get on Delta Math look like this. What is the image of 4, 2 given this rule? Not what I wanted to do. Given this rule. So when I look at that rule, I know that my x's are going backwards 5, and I know that my y's are going up 8. So that is the direction and magnitude of my vector, of my points. So what I want you to keep track of, we talk about a pre-image, and then we talk about that vector, what happens as a result that gives me my image. And if you'll look at these, we ask you for the image, the pre-image, the image, the image, the pre-image, the pre-image. So what you have to do is carefully think about what it is you're given and where that vector is going to result in your point moving around the coordinate plane. So if they ask me what is the image, that means that 4, 2 must be my pre-image. Because they're asking me what is the image. Are you with me on that? So if I have a point, that's over 4, 1, 2, 3, 4, up 2, what does my vector do to my x coordinates? Move it where? X coordinate. -5. What is my y gonna do to it? Move it up 8. So what's gonna happen is this point is going to travel along this vector by this taking away a 5 and this rising of 8. So they're asking me what are the coordinates of the image. So all I need to do is take 5 away from 4, add 8 to 2. Are we okay with that? Yeah.
Should we put the for the answer, should we put them in parentheses or the
Parentheses, because it's an XY ordered pair. Great question. The vector is communicated through the choppers, but the coordinates are XY ordered pairs, right? Parentheses separated by a comma. What's interesting about 8 is they switch it around. What's interesting about 8 is they're like, oh, hold on a minute, I'm telling you that the result of that shift was over -3 and down 4. That's the result. Where did I start? So what do you think I do?
The opposite.
Do the opposite. So instead of subtracting 5, what am I gonna do? I'm gonna add 5. Instead of adding 8, what am I gonna do?
Subtract.
Mackenzie's got it, subtract 8. Because it's gonna move along that same vector, right? So when I talk about this was done to this, where was I when I subtracted 5 and I ended up at -3? 2. Where was I that I started at a number added 8 and ended up at -4? -12. Trevor's got it. So when we talk about what was that pre-image, that came first. With your partner, go ahead through and talk about 10, 7, 9, and 11. Go.
Oh, really? I'll just do it.
How did we do?
Okay.
Okay?
Yeah.
All right, good. So we have a Delta Math that shows you how to do this, and we broke your Delta Math assignment into 3 assignments: translations, reflections, rotations. That's our translations. Turn the page. When we start talking about reflections, we want to think about that line of reflection that acts like a mirror, and that image is reflected in that line. The transformation is a reflection, and the mirror line is what we call that line of reflection. It's an isometry because it does not change the shape or the size. And there's some rules here. If the pre-image is on the line of reflection, then the image is itself. I'll show you what that looks like in a minute. If the pre-image is not on the line of reflection, then the line of reflection is the perpendicular bisector of the segment connecting the image and pre-image. And let me show you what we mean by that. So if you look here, this is my line of reflection between my pre-image and image. So do you see how this is reflected or flipped over? It's not always going to be vertical or horizontal. You see I have a diagonal line. And do you see that this line, this dot is flipped over the line? This green line is the perpendicular bisector of this red line. This green line is the perpendicular bisector of that red line. Perpendicular, 90 degrees, bisector, it's going to cut that line in half, and here's what's important. The thing that is reflected is going to be equidistant from that line of reflection. So this symbol, this chomper, is the same distance from this green line as this chomper, just in opposite directions, is reflected over the line. This dot is the same distance, and remember, distance is always measured with a perpendicular line. So that's why that perpendicular relationship is important, and the fact that it's bisected. So when we talk about drawing these, when we draw our reflections, if you look at each vertex in your figure and in your reflection, draw its reflection exactly the same distance from that line of reflection. So if I have this here, those red dots are equidistant from the line. This purple dot is going to be equidistant from the line. So then I can go ahead and trace to draw that shape that's been reflected in the line. That technique is critical when I have a diagonal line. So what I want you to do is think about each dot being reflected and as far away from the line along a straight line as you can make it. The further the dot is away from the line, the harder it is to get it right, but then you can have the orientation of that reflection. So number 3 is kind of fun. because that singular dot, if I reflect it in, remember that's the same as saying over. If I reflect it in my x-axis, I'm going to go ahead and draw that dot as far away from that line of reflection. So it's the same distance above and below. Everybody okay with that dot? If I draw its reflection in the y-axis, that's itself. How far is it from the axis? It's not. So guess what? It's its own reflection. And that conversation is what we're talking about here. When we talk about the reflection in the line y is equal to x, you're going to have to get good at drawing that direct variation with a slope of 1 that goes through the origin, because that line y is equal to x has 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2, negative 3 as solutions. And when I draw that reflection, it's going to be equidistant and land on that axis. We love this diagram. You will see it again with different questions. But we're going to use the diagram to name the image of segment 1 after each reflection. When I look at segment 1 and I reflect it in the x-axis, that's the same as over the x-axis, and that gives me segment 7. Are you okay with that? Talk to your partner about B, C, D, E, and F. Go.
Why would you do that?
So then it's with, so then.
How do we do? You want to talk about any of them?
I don't know.
Which one? Alright, oh, okay. So, let's talk about B. We'll just go through them all. For number B, I want a reflection in the y-axis, which is going to give me 2. Everybody okay with that? I want a reflection in the line y is equal to x. That's that positive vertical line with a slope of 1. So my reflection is going to be down here as number 4. Because this reflection in the line y is equal to negative x, y is equal to negative x, that line looks like this. So if I turn that around, see how that's itself?
Oh.
Do you see it? Yeah. A reflection in the y-axis, which is this way to 2, followed by a reflection in the x-axis, which is this way to 4. And then from 1 to 7, 7 to 4, both end up with 4. Here's something cool that ends up happening. When we reflect over a line of reflection and our shape changes orientation, the corresponding angles and segments maintain the same distances and the same angle measurements, but they wind up in different positions. So do you see here that this side length here corresponds to this side length? So we can ask you lots of questions like solve for D. And you would be justified in setting that up, because if you're told it's a reflection, you know it's isometric. If it's isometric, then the shapes stay congruent. Same size, same shape. So corresponding angles are going to have the same measure. So you know that 138 is equal to 3A. Corresponding sides have the same measure. So C is equal to 7. Corresponding angles are going to have the same measure. So B is equal to 95. So you can find the value of each of those variables by matching up corresponding. What does corresponding mean?
Same side.
Matching.
Matching.
Alright. Let's go again. A rotation is where I go ahead and I spin something around. A rotation is a transformation in which a figure is turned around a fixed point, and that fixed point is the center of rotation. That rotation is isometric, which means that my shapes remain congruent. So if you look at this shape here, if I have this center of rotation for my shape, I can look at the fact that I went ahead and rotated this shape 45 degrees counterclockwise. If you look at that shape, you can see that I rotated it up 45 degrees counterclockwise. It mapped onto itself. That's going to be my angle of rotation. That fixed point is my center of rotation.
What if they did like 225 degrees clockwise?
You can go ahead and play with knowing that 360 is the circle. So 225 this way is going to be 360 minus 225 that way. You know what I mean?
Right for 45. 225 that way.
Yep. All right, so here's some practice about this rotation, and I'll draw some pictures for you to help you with the first couple ones. If I'm rotating A and B of this shape, what I want you to do is I want you to think about a 90-degree clockwise rotation around that center P. So do you see how that ends up on segment CD? A maps onto C, B maps onto D. Are you okay with that? Go ahead.
What does it mean about P?
That means that's that center of rotation. So it's spinning with P being my center. Okay? Now, you don't have the ability to draw something and rotate it around on your screen. But what you can do is spin your paper. So if you take a look at the segment, everybody lock eyes on segment DE, and then I want you to spin your paper the way that they tell you, 90 degrees clockwise. So if you spin your paper 90 degrees clockwise, do you see how DE ends up in that orientation? So if one partner spins and one partner keeps their paper the same, you can be like, oh, DE is gonna end up where FG is. Do you see it when it rotates and spins? So that clockwise rotation of DE ends up where F and G are now. Are you with me on that? So here's something that I want to show you while we're talking about this. And this is your math space textbook. And you're like, math space? You guys did math space last year, right? I know, don't roll your eyes out. I promise this is okay. If you go into Schoology and you go into the Waffle and you log into Clever and do all that stuff that I hope doesn't bring back trauma from last year, if you go to our textbook, the textbook has this chapter here on rigid transformations. If you go to translations and go to the lesson, you can go ahead and see the widgets. And the widgets are actually pretty cool because they will show you, here's coordinate notation of this translation. And I think the widgets and being able to interact with them dynamically are pretty cool. Let's talk about the reflections. If you go to the reflections, it'll show you your line of reflection, and I can go ahead and change the slope of my line of reflection, and I can have it show me my image. So then I can have it show me the points and measurements if I wanted to. But what's crazy is as I move my slope, I can see my line of reflection changing. I'm trying to get it so you can see it all at the same time. If I try to go vertical, is it going to let me go vertical? No. As I go closer and further, I can see that reflected image. Here is my slope of +1, and here is my slope of -1. Notice this is its own reflection over that image. If you go to rotations, you can go ahead and you can see the coordinates. You can look at the rotation around that point of your shape. And you can change your shape too. So if I wanted to see what this shape looks like when it's rotated, I can ask it to rotate to 70 degrees, 180, 90 degrees. I don't think I can pick counterclockwise or clockwise. So Brady, that kind of brings back your question about, is it always counterclockwise or clockwise? So it's kind of cool to be able to see what ends up happening. I encourage you to go to MathSpace to play with them. In addition to MathSpace, we also gave you some. I love the Delta Math practice because the Delta Math practice allows you, we have translations, reflections, and rotations. So we, instead of putting them in one big assignment, we broke it all up into little ones. So for your translations, you can go ahead and look at the skills, and they guide you through. Just determine which translation would map figure K onto figure L. So figure K, so we can say a translation, if I want to go from K to L, I'm going to go left, how many units? I think 8 units, does that sound right to you? Did you count 8 or is it just me? So K to L has got to go left 8. And it's got to go up, how many? 1, 2, 3? Did we buy 3 units? 1, 2, 3. And then watch this. It lets you try it over. Oh, I went too many. So it's not left 8, it's left what? Uh-oh, where'd it go? It's left 7. So let me fix that. That's what I get for counting with my old lady eyes. Now we can try it again. How'd I do this time? Got it. So you are correct. You can press submit to get credit. That's all we ever want is credit. There we go. And it's kind of cool how it shows you. So I'd like you to visit Delta. I'd like you to visit MathSpace just to see those widgets are cool. But the Delta Math practice problems will give you that feedback that we like so much. All right. Last bit of conversation here. Go ahead with your partner. Talk about C, D, E, and F. Go.